We're going to be talking about ambiguous grammar and how to resolve it. The picture in the top left of the screen is an example of ambiguity. It can be interpreted as either two faces looking at each other or a lamp. So, explaining ambiguity. A grammar is ambiguous when two parse trees can be drawn from the same string. In other words, ambiguity results from one string having more than one meaning. So why is the following grammar ambiguous? E can resolve to E, E plus E, E times E, E divided by E, or some kind of integer value. As a result, the string 3 times 2 divided by 4 can be interpreted as 3 times 2 then divided by 4, or 3 times the value of 2 divided by 4. The string is perfectly valid in the context of this grammar, but has no other information to determine which of these interpretations is correct. In order to resolve ambiguity, we need a one-to-one mapping of strings to parse trees. So, using the example from the previous slide with the same grammar, we can see how this expression might evaluate. We start off with an E, evaluate that to an E times E, take the rightmost E, evaluate that to an expression, and then replace E's with different integer values, resulting in the following parse tree. Or, we can have our initial E, resolve that to E divided by E, take the leftmost E, resolve that to E times E, and then plug in our integer values, resulting in the following tree. As we can clearly see, the exact same string results in two different parse trees.
And now we'll move on to resolving ambiguity using BNF grammars. The following examples you'll see will be used to define right and left associativity, as well as precedence of binary operators. Associativity defines in what order a sentence will be evaluated, right to left or left to right, whereas precedence revolves to which operators will be evaluated before others. So our first example is that of a right associative grammar. As you can see in the parse tree on the right, an example sentence created from this grammar creates the sentence 1 plus 2 plus 3 plus 4. Notice that this same sentence can only be created from this one parse tree. Due to the defined grammar, we then see that this gets evaluated starting with 3 plus 4, and then plus 2, then plus 1, proving this to be a right associative grammar. Next we have a left associative grammar. Notice that this creates the sentence 4 plus 3 plus 2 plus 1, also created from this one and only parse tree. We see again that this will be evaluated in a certain order, this time starting with 4 plus 3 on the left, then plus 2, and then plus 1. This is defined as left associativity. And now we'll take a look at a grammar showing precedence of binary operators. From this grammar, as we can see in the parse tree on the right, we get the sentence 0 times 2 plus 1 divided by 4 minus 3. By looking at the parse tree and the grammar syntax, we find that multiplication and division will be evaluated first, followed by addition and subtraction. Therefore, multiplication and division have precedence over addition and subtraction, giving us the order of all operations that we all know and love.
An alternative method for resolving ambiguity in grammars is to write two grammars that use parse trees directly. This way, expressions must be coded in such a way that forces parentheses, so the precedence and associativity of operators is not an issue. This way, ambiguous expressions cannot be written. For an example, we can write a grammar for a simple arithmetic expression without ambiguity. The starting token of the grammar is the letter E, which will represent our expressions, and the token N will represent any integer value. To show how this eliminates ambiguity, consider how we would write the expression 2 plus 5 times 6. As we know, this is ambiguous because we do not know whether to combine the 5 and 6 first, or to combine the 2 and 5 first. If we wanted to combine 2 and 5 and then multiply by 6, we would start with our starting token, and as you can see by this derivation, we would reach the expression times of plus 2 and 5, and 6. Alternatively, we could combine the 5 and 6 first, and then add 2, once again starting with the starting token E of the language, and by this derivation producing the expression plus of 2 and times plus 2 and times of 5 and 6. In the Scala programming language, we can easily represent a grammar like this by using a class. In Scala, classes are recursive data structures that can contain multiple case classes within them. To represent arithmetic expressions, as in the previous grammar, we could write the following. First, a sealed abstract class that we call expr for expression, then a case class n for integers, and 3 more case classes, plus, minus, and times, that will represent addition, subtraction, and multiplication. Each of these will take 2 arguments, a left and a right argument, each of which is also an expression. As an example, we could write plus n3 plus n5 n18 as shown, which would be equivalent to the expression 3 plus 5 plus 8, where 5 and 8 are first combined and then added with 3. Although this grammar will eliminate ambiguity, a downside to writing expressions this way is that they can be very tedious to write. For example, this lengthy arithmetic expression would have to be written as such. As you can see, the top expression is much easier to read and much easier to write because parentheses do not have to be explicitly indicated.
An example of ambiguity in C is x asterisk y. This can be interpreted as a declaration of y as a pointer to type x, or the value of x multiplied by the value of y. To resolve this ambiguity, the compiler will consult a symbol table for type x. If type x exists, the above statement is parsed to mean y as a pointer to type x. Otherwise, the compiler defaults to a multiplication statement. However, it is not always this easy to resolve ambiguities. The problem of whether or not a grammar is ambiguous is undecidable. Most ambiguities cannot be resolved by a deterministic parser. These two problems pose a particular challenge when processing natural language. Natural language is inherently ambiguous. This means that it can only be defined by an ambiguous grammar. More specifically, natural language can be represented by a context-free grammar. This was proposed by Noam Chomsky in the 1950s. He chose context-free grammars to represent natural language because CFGs, or context-free grammars, allow for recursive definition, and as such they were a good tool for representing the grammar of natural language. To further improve the recursive capabilities of CFGs, Chomsky normal form was developed. A grammar in Chomsky normal form has the following production rules. X goes to YZ, or X goes to lowercase x, or epsilon, where X, Y, and Z are non-terminals and X is a terminal. To better understand the structure of languages, linguists often place logical parentheses within a sentence to place a sentence into its block structure. So for example, John walked to the store would be parenthesized as follows. It's now easy to see the advantage of comprehending language as a CFG, because CFGs allow you to parse matched sets of parentheses. The parenthesized sentence, John walked to the store, can be parsed using a stack-based approach. Left parentheses, when encountered, are pushed onto the stack. When a right parenthesis is encountered, the top element of the stack is popped. This type of parsing allows the sentence to be properly broken into its blocks. Groucho Marx's famous quip, "I once shot an elephant in my pajamas." It cannot be parsed using the stack-based approach. It's ambiguous. The sentence could either be interpreted as, "I once shot an elephant while I was wearing my pajamas," or "I once shot an elephant that was wearing my pajamas." To resolve this kind of ambiguity, a probabilistic approach can be used instead of a stack-based approach. This approach would assign different probabilities to parsing options, and then the most likely parse tree would be selected. Therefore, the likelihood of an elephant wearing someone's pajamas is very low, so it would be unlikely that that particular option would be selected in parsing the sentence.